I'm a physicist, not a mathematician, and you're just supposed to know. So I is going from whatever the first value is to whatever the last value is. Now let's take the next step. There is not the speed. I'll try a complete sentence this time. The speed of every particle here is not the same. This was the hassle we ran into. What do we choose for V? But there is something common to every piece in the door. And it was sort of alluded to before. What is common to every part of the door?
The angle is 1%.
Yeah. So in 2 pi radians, it goes 3 seconds. So every part of the door has the same angular speed, which in this case is 2 pi over 3 radians per second. So if I can express V in terms of omega, we got something there. And we have discussed this when we were dealing with centripetal motion. This is where I want it. What is the relationship between the speed of a part of the door and the angular speed? There's an equation we used to come up with our alternate formula for centripetal acceleration. Or we could just derive it again.
1/2 I omega squared.
Not that.
Oh.
We're deriving that, but not deriving that now. All right, let's go back to the drawing board here. All right, the speed, right there. That is the speed of any part on the door, which is the same as 2 pi over t times r. That is just omega. Oh, keep forgetting. So what we have here is V equals omega r. So what I'm going to do is I'm going to substitute out VI for that. Now omega is the same for everything, so it doesn't have a subscript. R is different, so this becomes 1/2 times the sum of MI omega R sub I squared, which is just 1/2 times the sum M sub I omega squared RI squared. I'm now going to take that omega squared and just, it's a constant. Every term has it, so I can just factor it out. So what I end up with is 1/2 omega squared times the sum of all the MI squareds. And I'll go ahead and stick the I equals 1 to n there. So as n goes up, the mass of each object gets smaller and smaller and smaller. R doesn't necessarily, R just is whatever the distances are. Now this is almost where we want to end up. This actually is nicer than what we had. It might not seem like it because, well, frankly, we want to break it up into an infinite number of infinitesimally small pieces. And you might think, well, if I'm doing this by hand, that's going to take me a lifetime. And then some. However, this is already known. Or, take that back. This has a special name. The symbol for it is capital I, and this is the moment of inertia. There's a more formal name to it, which I'm blanking on right now. Some textbooks will call it rotational inertia. But if that is our moment of inertia, then our kinetic energy is 1/2 I omega squared. The formula we wrote on the board 2 days ago, and the one that Stone mentioned about 3 minutes ago. So 1/2 mv squared is captured in this. It's just, this is a shortcut, if you know what I is. So how do you know what I is? It depends on the shape. All right, first off, I don't have the textbook sitting in front of me right now, but and actually the version I have printed out is a different version probably than the one you have. So the page numbers are off. But your textbook has a page where they've already done the calculation for capital I for certain common shapes.
So like, what about a sphere?
Say it again.
A sphere.
So if we have a solid sphere, rotating about a central axis, the moment of inertia is, solid sphere would be 2/5, thank you, m/r squared. Now notice I have a capital M and a capital R there. This is tradition, because using the lowercase m, lowercase r for a specific point, and capital M for the mass of the entire thing, R for the radius of the entire thing. Now sometime I might write a lowercase m and lowercase r, but I'm doing capital I's just because that's the way textbooks usually do it. If it is a hollow sphere, rotating about a central axis, gives some sort of sense of sphere there. A hollow sphere, or thin shelled sphere, the moment of inertia is 2/3 m/r squared. If I have a rod rotating about a central axis like that, so thin rod, the moment of inertia is 1/12 ml squared, where L is that length right there. Notice that all of these are rotating about an axis that goes through the center of mass. I'll do a couple other ones and then I'll go back to addressing what if it doesn't go through the center of mass. I have a disk, the moment of inertia 1/2 m/r squared, rotating about an axis, basically in and out. If I have a hoop rotating about a central axis, that is hoop, not loop. Moment of inertia is just squared. And it turns out, if I have a disk rotating, so if I have a disk rotating about that axis, it's also 1/2 m/r squared. And it's just coincidence that it happens to be the same formula in either case. All right, questions up to here before we start tackling. What if it's not rotating about a central axis?
Wait, what's the last one?
This one or that one? This one?
Yeah.
A hoop. So I've got, pretend the spokes are not there, so basically something like that. generic shape. Rotating about this point, so this is the axis of rotation. This is the center of mass. So if I want to find the moment of inertia of some object, some generic object, I know that the moment of inertia is the sum of all the, not more uppercase there, all the m sub I r sub I squared. So I want to take some point right there. We'll call it point I. That would be r sub I. I know that the center of mass there, I'm just going to label that r sub c. Because again, we're doing everything in reference to the axis of rotation. And this I'm going to label as RIC. So it's basically the location of I with respect to C. These are vectors. So R sub C is equal to, R sub I, and I can get that. All right, R sub I is just R sub C plus R sub IC. So this would be m sub I times, well, Ri squared is the same as Ri dot Ri. So any vector that does a dot product with itself is just the magnitude squared, which is the sum of m sub I times Rc plus Ric dot Rc plus Ric. So I'm going to do a little FOIL here. So I is equal to the sum m sub I times Rc dot Rc, then outer plus Rc dot Ric plus, well, actually two of those, and then plus Ric dot Ric. Dominic?
This might be a dumb question. Is that sigma notation or a different symbol?
That's a sigma notation.
Okay.
I feel like this section is missing pages. All right, we'll see how far I can get before I go, wait a second, there's a mistake somewhere. So far, so good. So that is just the position of the center of mass squared. It's a vector dot product with itself. So this becomes the sum of mi rc squared plus the sum of m sub I rc dot ric plus the sum m sub I ric squared. Take a look at that first term. that is, well, R sub c, I have an axis rotation, I have a center of mass, R sub c is a constant. No matter where I am, RC is always the same. So if RC is a constant, I can factor that out, and I'm left with just the sum of all the little mi's, which is just the total mass. So this becomes R sub c squared times the sum of all the little mi's, which is just R sub c squared times m, total mass. This last one, that's just the moment of inertia rotating about the center of mass. That's I. I put a little c there to represent, this is the moment of inertia with the axis going through the center of mass. So we've got this pesky little term right here,
Where did the 2 go?
where the, oh, you were correct. Stick it out front.
Is there a reason that the ones you have circled, there's just not a vector for the R's?
Dot product is a scalar product.
Okay.
So I have a vector dot product with itself, it's just the magnitude squared, so it goes away.
Okay.
Ultimately, RC dot RIC is a vector. Oh, sorry, it's a scalar.
But because you can't combine them,
Not easy. Not
mathematically, they're still vectors.
Yes,
Okay.
because I haven't combined them yet, they're still vectors.
Okay.
So I need to somehow figure out what is the sum m sub I R sub c dot R sub IC. Alright, so R sub c here is a constant. What we're gonna do is I'm gonna sort of flip it around a little bit. This would be the same as R sub c dot the sum of all the mi RICs. And m sub I RIC is the sum of the masses times the positions of every spot with respect to the center of mass. Well, if you think about what the center of mass actually is, that means I have just as much mass on one side as I do on another. It balances out. Slight hand waving here. That equals 0. Because I'm going to have, if we imagine, take a simple shape like a circle, I got my center of mass here. If I'm looking at some tiny little mass there, I've got mass times that vector. There's going to be one on the other side. That when I add them together, I'm going to get 0. This is going to balance out when finding the center of mass. And there's a 15-minute version of justifying that, but I'm hoping you can sort of take the concept and run with it. So if the sum of all the MIRICs is 0, then this whole term becomes 0, and that disappears. So what I'm left with, the moment of inertia rotating about some point P is the same as the moment of inertia rotating about the center of mass plus the mass times how far we have shifted the axis, which looks typically right leave with an H. H is it's the way I picture it in my mind's eye. This is known as the parallel axis theorem. Not sure why it's a theorem, but it's called the parallel axis theorem. I feel like it should be the parallel axis definition. So if I took my thin rod, and instead of rotating about the center, I rotated about the end. So for those who need the visual, oh, there's the rod. So instead of rotating about the center here, I'm now rotating it about the end. Well, the moment of inertia then, let's make it a darker color than that. The moment of inertia rotating about the end is going to be the moment of inertia rotating about the center plus mh squared, which is 1/12 ml squared plus the mass times, well, I shifted the axis from here to here. So instead of the rotate, that's how far I shifted the axis. It's parallel to it. So I'm not going from here to something going that way. It's parallel. And I shifted it half the length, L over 2 squared, which is 1/12 ml squared plus 1/4 ml squared. And 1/12 plus 1/4 is 1/3. And some textbooks will give us